So welcome back. We almost got to the end of the last lecture on tricks with trees. And so let me just remind ourselves of how far we did get, and then I'll finish it. So we started by saying that anything you want to do in parallel, as long as it depends on n inputs, is going to take you log n steps to do it. Because after one time step, you can depend on at most 2 inputs. After 2 time steps, you can depend on at most 4. So it takes you log n time steps to depend on n. So the question is, what can we do usefully in log n time steps? And we had a whole long list of examples. And one of the reasons I'm telling you about this now is that the next part of the lecture will be about MPI, a programming system that you'll use a lot. And many of these functions are built in because they're so commonly used. So the simplest thing is a reduction. Everybody has a number, and you want to compute the global sum and let everybody know. That's called a reduction. Any associative operation would work for that. And the converse, if you like, is broadcast. One processor owns a number, wants to tell everybody. So that's a tree as well. Those were the 2 most basic ones. But the next one, which was a little bit more surprising, was parallel prefix, in which case you have an array of numbers, and you want not just the global sum, you want all the prefix sums. x1 plus x2, x1 plus x2 plus x3, and you can do all that in, well, 2 log n time. And so based on that, I gave you a whole bunch of examples, some of which are used in every computer that's been built for decades. That's how integers get added. In that case, you can add 2 n-bit integers in log n time, and the associative operator is 2 by 2 matrix multiply with Boolean matrices. So it's all associative, and it all works. And then there were lots of other funny examples, too, some of which were just gee whiz because they're completely numerically unstable. But you can do it. And so what I want to do today is finish and give you 3 interesting practical examples where this comes up. One from an image segmentation problem, one using to implement sparse matrix vector multiply, and another one which is being implemented in various browsers, and it's how you figure out where to put the stuff on the screen. So page layout. And there's many, many more examples, but I'll just do these last 3. So let me now move ahead to that slide. So image segmentation is one piece of a bigger problem, which is image recognition. What you'd like to do is say, I have lots and lots of pictures on my cell phone, and I would like to automatically find all the pictures that contain my pictures of my friend Fred. Right? I think there's an app for that already. But one of the things that's built into it to make those applications work is you have a complicated image with many things inside of it, and you need to break it up. You need to find the contours, the boundary lines between one part of the image and another. So here's a picture of a bear. Here is what human beings do. So the way this field works is you get lots of people to spend their time saying which pixel's on the border between the bear and a tree, or between the bear and the branch. And this is what people do. And here's the output of the automatic algorithm, which does a pretty good job of agreeing with what people do. The point is, how do you decide what the right answer is? You get this human data. And so the algorithm I'm going to tell you about is one piece of a bigger algorithm, which is widely used by, it was developed by Jitendra Malik, who's one of the computer science faculty here. And so I will tell you what the bottleneck is and how to fix it using parallel prefix. So let's think of the image as a matrix. So for each ij, you get a pixel. And each pixel has a quantity associated with it, how much red, how much green, how much blue. And so the bottleneck in Malik's algorithm is to identify for each pixel whether it's likely to be on a contour or not. And then, of course, you have to piece together the pixels to create the lines. But right now, we're just going to go pixel by pixel and say, are you likely to be on the border between one part of the image and another? And so here's a natural way to start. So let's look at that pixel with the X on it right there. What we're going to do is compute, let's say, the average red intensity of some box of pixels, 4 by 9 box of pixels above that point. Then the average red intensity of all the pixels below that point. So obviously this has a higher red intensity than that. And then we'll subtract them. And we will get a large number associated with that particular pixel. We'll get a small number associated with that pixel because it's about as red above and below, and ditto for that one. So this one will get identified with a large number. And so what I'd like to do is compute another matrix. So the input is a matrix of all the red intensities, and the output is for each pixel the difference between the average red intensity above and the average red intensity below in some little boxes. So I'm going to take a big matrix as input. I want to get a big matrix as output. Then the next part of the algorithm, which I won't talk about, is what do you do with this matrix which says you're likely to be on a boundary or not? That turns into a graph partitioning problem. I've mentioned that one before many times. This is yet another application of graph partitioning, and we'll have a lecture on it later. So right now, the bottleneck, my goal is I'm given a matrix of red intensities, and I want to compute the difference between red above and red below. So here's the bottleneck. And I'm just sort of defining some notation again. So here's all my pixel values. This is the output that I want, the difference in red above and red below. So what I'm going to do is for some small value of k, it was 4, so I get a 4 by 9 rectangle before. I want to compute the sum of all the red intensities above the pixel ij, the sum of all the red intensities below, above and below, and then take the difference. And so the question is, how do I do that without doing, well, if it's an n by n array, I might need to do n squared work, but if it's a k by k box, it would be n squared times k squared if I just did each one independently. I want to do it much, much cheaper than that. So here's the trick. Let's suppose that given my array A, I could compute very quickly the sum for all points of everybody to my left and above me. So my input is an array, A, and I want the output, S, to be the sum of everything from 1, 1 up to ij. So everything in the dark gray box, in the dark box there. Let's suppose I can compute that quickly. But what I want is the sum of any particular rectangle, right? I want these little k by, 4 by 9 rectangles. So let's suppose I just had the sum of all these big boxes, but I wanted that. What would I do? Well, I'd start with the sum of all that. Then I'd have to subtract out the parts I didn't want. So I could subtract out that rectangle. I think the boundary is green. And so I would get rid of that corner, but I'd still be left with this. So I have to subtract that out. So I subtract out the sum of everybody in that box with the red boundary. So now that's gone, but I've subtracted that out twice. So I better add it back in. And so now I add back in the sum of that box. And with 3 or 4 more additions, I've gotten every box that I want. So instead of the cost being order n squared k squared, it's order n squared. Okay? So the trick is, how do I very cheaply compute all of these sums that belong in here? Okay? And it's all parallel prefix. So are there any questions about this slide? So the new bottleneck is I'm given this original matrix, n by n matrix A, and I want for every ij the sum of everybody from the top left corner down to the ijth entry. So what I'm going to do is two-dimensional parallel prefix. So the first thing I'm going to do is for every row, independently, I'm going to do a parallel prefix sum from left to right. So for the first row, I'll compute the leading sums of all of the leading guys, so up the first j entries, for example. I'll do that for every row. And then I'll take that, and I'll do parallel prefix down the columns. And so this guy, so what number do I get here? I start with all the sums of everybody in the first I rows down to the jth column. Then when I sum those, I'll get the answer that I want. And so you get two-dimensional parallel prefix, and everything works well. So, and that's, you can imagine that gets implemented widely. So are there any questions about this example? That's all I wanted to say about it. Yes, and there's a microphone, I hope.
What's the reason to store all the prefixes and not just sum across and then sum down the last column?
Well, I want the value, the sum S, for every box, starting with the 1, 1 corner down to the ijth. So I need to compute all of the n squared partial row sums, and then I do all the n squared partial column sums of that. And what I'm left with is, for every ij, I get the value, the sum of everybody to my left and above. Next question.
Is 2D parallel prefix a common primitive that's implemented in libraries?
No, I think this one was implemented by hand in CUDA for the GPU implementation. And we'd have to ask Brian, who will be giving a guest lecture later in the semester, as to exactly what the implementation looked like. But from a high-level point of view, it was lots of independent row-wise parallel prefix followed by lots of independent column-wise parallel prefixes. Okay. So let's go on to the next example, which is only one slide. So again, I'm going to just change parallel prefix very slightly and get it to do sparse matrix vector multiply. And so this is called segmented scan, so it's a slight variation on it. So here's the idea. Here's the set of numbers in which I want to do parallel prefix from left to right. But in addition, I have an array of true and falses that tell me every once in a while I like to start over. I'd like to restart the sum at 0. So here, true says I start summing here. So I get 3. False says keep going. So I get 3 plus 1 is 4. False says keep going. 3 plus 1 plus 4 is 8. So those are the prefix sums of the first 3 entries. True says start over. So forget what you've done before and start over with a 5. And that's what I get. True says start over again. So I start with a 6 and I get a 6. But now I keep going. So I get 6 plus 1 is 7. 6 plus 1 plus 2 is 9. And finally, the last one is I start over at a 3. So there are 2 inputs, the usual array of numbers and an array of true falses. So how do I do sparse matrix vector multiply using that particular primitive and assuming it's implemented quickly? It'll make sparse matrix vector multiply go fast. So here's my data structure, which I showed you before. Let me show it to you again. Here's my sparse matrix represented with all the zeros that I don't want to store or do any work with. So what I'm going to do is take all of these non-zeros and pack them into an array, just row-wise, throw out all the zeros. So 1, 2, 3, 2, 4, 5. 1, 2, 3, 2, 4, 5. I have to remember what columns they came in. That's the column index. So there's column 1, 3, 4, 1, 3, 4. And then I have to remember where each row begins. So that starts at the first entry, the fourth entry, the seventh entry, and then there's a pointer off the end. Say the 9th row, if it existed, would be there. And then finally, there's my vector x against which I want to multiply all these guys. So what I'm going to do for starters is take all these values, matrix entries, and multiply them by the appropriate x entries, because I have to do aij times xj. So let me do all those. So I'll have 1 times 7 is 7. 2, that's in the 3rd entry, so 2 times 2 is 4. 3, that's in the 4th entry, so 3 times 1 is 3. All that's embarrassingly parallel, and these are the numbers which are the individual products that I need to sum up row by row. So now it's going to be one operation. It's going to be segmented scan. I just have to say where do the rows begin. Put a little true where the beginning of each row is, and then put falses as I want to sum up each row. So the first row of a times x is going to be 1 times 1 plus 2 times 2 plus 3 times 1. So I want to do my first partial sum by adding up those numbers. So I do true, false, false. And 14 comes out the answer. Then the next row has another 3 entries in it, 2, 4, 5. So I have true, false, false to add up the 14, 32, and 51. And I get a 61. And then the last one just has 2 entries, and out pops the final sum there too. And then I just extract the 3 entries, and there's my final answer. So it's a perfectly natural fit there too. And you can read about people implementing this in that website at the bottom. So here's yet another generalization. So the last generalization, we do 2-dimensional. Here we have start over occasionally, do it in segments. And there's one more generalization where people do this. So the original way I described parallel prefix was you have a binary tree, and you want to sum everybody to your left in the binary tree. And I said there is a simple algorithm where you go up the tree, leave behind the sum of everybody of your left child, and then go down the tree. Well, there's nothing special about a binary tree. I could do that to any tree. And that's how page layout in a browser works. So what we'd like to do is very quickly, you have an HTML program. That's the low-level program in which all web pages are written. And it has this complicated nested structure that says, here's an image, it consists of other images, they fit inside one another. You need to figure out where to put each one. You need to figure out the pixel coordinates to put each sub-image. And the simplest example would be, let's suppose I just had a bunch of images from left to right across my screen, just one-dimensional, and I knew how big they were. That's part of what HTML specified. So my first image on the left, that's x1 pixels wide, the next guy is x2 pixels wide, the next guy is x3. So how do I figure out where the ith image goes? Well, I start him at pixel, sum everybody to my left, right? And then I know that's where the jth image will go. And that's exactly what a prefix sum does. But now it's much more complicated because each of these images could be itself a collection of images. And it's not just in the x direction, it's in the y direction. And so what I do is I have a rather general tree which says that each image consists of some other images. I run the same parallel prefix algorithm. I keep a little local sum of everybody to my left, except now I have to do it for both the x coordinate and the y coordinate. I traverse the tree a few times, and out pops the location that every image goes in. And this is work done by my colleague Ross Bodick, and and his student Leo, and they're busy talking to a number of companies who are interested in implementing this because this turns out to be a bottleneck in a lot of browsers. So let me just summarize. Are there any questions about this? So let me just summarize about trees. So lots of problems can be done quickly, at least in theory, using trees. And sometimes you have to be a little clever about what the tree looks like and how to break it up. I tried to give you lots of examples. Some of these algorithms are so widely used, like broadcast and reduction and parallel prefix, that they're everywhere, including every computer to do addition. And also, they're going to be in the MPI library I'm going to tell you about in the next part of the talk. Some were of theoretical interest only, and I guess the takeaway here is that not every fast algorithm is a useful algorithm. It has to give you the right answer too, despite round off, and I just gave you some fun examples there. And these operations have been built into many systems, not just MPI, which is now a standard available everywhere, but there's a long history of people building parallel prefix operations into many previous languages. So are there any questions before I leave this topic and give the floor to the GSIs for a moment to talk about logistics? But questions? Okay. And you go ahead while I switch.
All right. So the Homework 1 results are available online on the Homework 1 page. So you're welcome to take a look there and see if anyone else has similar interests to you and would potentially be a good project partner. And if you don't have a homework listed there, then we never received one from you, and you should contact us to... Homework 0, yes.
Yes.
And then...
it's a zero-based course. We use C as the example all the time. Yes.
Of course. Homework 1 is due a week from today, so make sure you can log into Hopper and compile the benchmark code.
Except
today. Except today, because it's down. So try that tomorrow. And we suggest you start looking, if you want to get started on a few optimizations for the code, we suggest looking into compiler intrinsics, as well as cache blocking and copy optimizations that allow you to align your data and use special intrinsics instructions. So any questions on homework 1?
On Thursday, so we want you guys to really think about it, but on Thursday we'll also give some hints in class, and if you want any more help, just come by office hours, kind of talk about some high-level kind of, I'm going to call them compiler tricks, but they're optimization tricks in general for making code like this a lot faster.
Okay, thank you very much. So the rest of the lecture, and I may not quite get to the end today, is to talk about distributed memory machines and a little bit about what the hardware looks like, and then a simple mental model so that you know what's fast and what's slow. So when you write code, you'll write efficient code. And then the actual programming system language that you use on top of it, which is MPI, Message Passing Interface. So just to recap what we did at the beginning of the last lecture, we did told the same story for shared memory machines. And in that case, they had caches which stored shared data. And the caches themselves could either be shared, so whenever a processor did load location 37, they all went to the same place, or they were distributed, but in that case, everybody who refers to location 30, the same variable A, and it's shared, wants to have the same value. And so there has to be some mechanism in those machines to keep it coherent, so that if everybody has a copy of location 37, they all have to be the same thing. And that is very hard to scale up. And there has to be special hardware, for example, so that if one processor updates that location, everybody else finds out about it right away. And there's plenty of courses that you can take if you're interested in figuring out how that stuff is built. But the takeaway is it doesn't scale up to very large machines. You can't get past tens or perhaps hundreds of processors. The largest machine I know of is 512. And so the only way you're going to scale up to a machine like Hopper or even smaller machines is to program in a different style, which is today's lecture. So I'm going to start off by telling you about distributed memory architectures, where there is no shared memory anymore. Everybody's, when you refer to location 37, you only get your version. You have your own private memory. And talk about a little bit about the hardware, in particular, how are they connected to one another? So how does one processor communicate and synchronize and so forth with another? And then give you a very simple performance model to have in your head so that when you write code, there's really only a couple of numbers you have to remember that model what the behavior of the hardware is. Then I'll tell you about the actual programming model, the code that you write. It's MPI. There's very long manuals. There's hundreds of different subroutine calls. You only really need to know 6 to write code that works. You need to know more if you want to optimize it, but there's sort of 6 subroutines to call to deal with the synchronization and the communication and so forth. And so I'll tell you about the basic sends and receives, like it's mailing letters to your neighboring processors. That's how you communicate. And sometimes you can do it without blocking. Sometimes it's blocking, which means you have to wait for the data to arrive. And there are those collectives, parallel prefix, broadcast, and reduce. So let me just put up one picture to indicate how common these machines are. So here's a picture of the top 50 fastest machines in the world from 1993 up until 2010. And it's color-coded by what fraction of the 50 fastest machines in the world had different architectures. So way back in 1993, there were a few single processor machines, but they disappeared. And if you look out here, it's kind of stabilized that everything is either this blue architecture or this pink architecture. And what are they called? They're either called clusters or MPPs. They're basically distributed memory machines. What's a cluster? That means you buy a bunch of off-the-shelf processors, your favorite Intel processor. You buy an off-the-shelf network, which could be an Ethernet if it's very slow, but people build many faster ones, and you just glue them together. And that is currently about 20%, I think it's 20% of all the machines. So as of 2012, the clusters were 82% of all the machines. And the other flavor, which is programmed exactly the same way, are called MPPs, or massively parallel processors. It's just the same thing, except it's all custom hardware. Custom processor, custom network, and this is just the historical data where people have it. So this is by far dominant in what big machines look like. So let me give you some history about how these machines are built. And I'll, again, dive into a few details and then give you a simple abstraction at the end. Question?
Can you remind me what a constellation is?
So a constellation was a funny machine. It's still a cluster, except the number of it was a cluster of shared memory processors. And the number of cores per shared memory processor was bigger than the number of shared memory processors. So those didn't scale, right? Because an individual shared memory processor is limited in how many cores it could have. So those kind of disappeared. You can see there aren't very many left. So these are of historically interesting names, right? But from our point of view, everything is a distributed memory processor at the end. That's all you got to know. Okay, so here is historically how these things were built. They were just a collection of off-the-shelf microprocessors connected with nearest neighbors using queues. So here I have a simple picture of 8 processors colored in blue. Each one is connected to its 3 nearest neighbors in the corner of a cube. And each of these connections is basically a wire that goes in both directions. And each wire implements a queue. So what this guy can do basically is put a bunch of messages intended for this neighbor in the queue. It's just a mailbox. They pile up. So here he has 2 pending messages being sent from that corner to that corner. And this processor is in turn sending messages back to him. And this processor's job is to every once in a while go open the mailbox and see if something's there and deal with it and take it out. Right? So it was a very straightforward done. The CPU was responsible both for all the useful work of arithmetic plus being the post office. Now, suppose this processor wanted to communicate to this guy, not to its nearest neighbor, then each of these would have to have a forwarding address. Each message would have a little header on it, and the postmaster here would have to read that, figure out where it's going, and forward it many times as needed. And so there was so clearly this was very time consuming to do that in these early processors. So people spent a lot of time thinking about exactly what should the topology be. This is a cube. People built hypercubes, higher dimensional cubes. They did a lot of experimentation to sort of minimize the number of hops to get from one processor to another in any particular algorithm. And that's become less important because the topology, people try to hide it in the hardware. So there's a separate processor that plays the role of the postmaster. But there's still some algorithms where if you don't pay attention to the topology, it won't go very fast. But that's sort of, if you really want peak performance. So what I want to do now is give you the 2 most important numbers to think about to model in your head about how fast a network goes. And so think of a network as like a street, in a city. And so each of those links between processors is a street. Each place where they come together is an intersection, so there's a switch there that has to figure out where to forward them. The distance from one place to another is how many hops, how many wires you have to travel along. And there needs to be an algorithm to decide how to get from one side of the machine to another, so there's a travel plan. And so the two numbers to measure this are going to be the latency and the bandwidth. So the latency is basically how long it takes for one message to go from any one processor to any other. And in the case of a street, you ask, I start driving one car, how long does it take to get somewhere else? You take the number of miles, you divide by the speed, and that gives you the number of hours it takes, right? So that's the latency. But the other metric is bandwidth. And that is, in the car case, how many cars per hour can you pipeline from one processor to another? That's a different metric. So in the case of cars, well, it depends on how many cars per mile get packed together along the street. It depends on their speed, of course. And it depends on parallelism. How many lanes, how many wires do you have to move the cars from one place to another? And so network bandwidth is going to be limited by the bit rate, bits per second, and the number of wires. So if you're sending very, very large messages, and we'll see data later in the talk, bandwidth tells you everything you need to know. That tells you how long it takes to get a really big message there. But if your algorithm is only sending tiny little words, one-word messages from one processor to another, you're going to be totally limited by the latency. And that's going to be your dominant term. And so it depends on your algorithm. Sometimes you can be clever and modify an algorithm so it sends a few large messages instead of lots of little ones. That's a design goal. And sometimes you can, sometimes you can't. So here are the design characteristics of a network. So these are what the hardware looks like, and they can also affect the way you write code. So who's connected to whom? What's the topology? And when I showed you the first example there, it was a three-dimensional cube. The first things people tried to build is a crossbar. That's where everybody's connected to everybody. That would be wonderful, right? But if you have P processors, you need basically P squared wires to have a crossbar. It doesn't scale, and so you can't really build a large machine that way. At the other extreme, you have a ring. Everybody's just connected to their left and right neighbors in a circle, and that's very cheap. You only have P wires, but there's obviously a lot of, you get a lot of traffic jams if everybody has to travel on the same road. What people do today is that they build meshes or toruses. So 2D meshes where you're connected to your four neighbors, north, south, east, and west, three-dimensional, and then higher dimensional. So Hopper is a three-dimensional torus. And so, and what's the difference between a mesh and a torus? I'll have a picture later, but in a torus, when you get to the top, you're connected around to the bottom again. And so Hopper and many current machines are three-dimensional tori. The old IBM Blue Gene Ls and Ps were 3D tori. But the latest one is a five-dimensional torus, so the IBM Blue Gene Q. So these are all sort of trade-offs, people trying to figure out what the right way to build it is. So a hypercube, that's sort of a special case of a torus where you only have processors at the corners. Early machines were like that. A tree seems perfectly natural. Of course, if everybody's trying to get from one side to the other and the root becomes a bottleneck, you have to deal with that. I'll show you how you deal with that. And then there's some other funny things called butterflies and perfect shuffles. And when we talk about the FFT later in another lecture, you'll see these were invented basically to make FFTs go fast. And they're useful for other things as well, too. But FFT was the original motivation. So you need an algorithm also. If you're on one side of the machine, how do you get to the other? And so a very simple thing to do in a two-dimensional torus, you want to make sure there are no traffic jams, one processor trying to deal with lots of incoming and outgoing traffic. So the simplest thing you can do is that everybody who wants to go east goes east. You're not going to ever have a conflict there. Then everybody who wants to go west can go west, and then you just sort of cycle through all of your connections, and that certainly avoids any deadlocks. It also sort of doesn't use all the wires all the time, and so you can sometimes do a lot better by using all the wires all the time. Then there's a question of how the switching strategy goes. And there's basically two models, the telephone and the post office. And basically the post office wins. So circuit switching is where you have to set up a connection from all the way through all the wires. You have to reserve them from one side of the machine to the other, and then your message goes along without any interruption. That's circuit switching. But what people do instead is packet switching, where you take your message, and if it's really long, you might have to break it up into little packets. And they all get forwarded, and they may all take different paths, but they eventually all arrive and get put back together at their destination. Indeed, that's how the internet works. So this is the standard way to do it. And then you have the problem is that if everybody's trying to talk at the same time, which isn't so unusual, you're going to get congestion. right? You'll get a limit on how much stuff you can push into the wires. And so what the processors have to do is basically stall. You have to wait until things clear out, and there's lots and lots of different algorithms to do that. You may need extra memory to keep track of it, and fortunately this is all hidden by MPI, but it's happening underneath the covers. So here, let me tell you about what properties of a network affect the latency costs, then I'll show you some numbers. So so think of the processors as forming a graph. There's one vertex or node for every processor, and a wire and an edge for every wire. And so the simplest metric of what that graph looks like is its diameter. What's the longest path between any two vertices in the graph? And if you always send messages between the two vertices that are farthest apart, that's the slowest thing you can do. So that's called the diameter. And so you're going to have to pay at least the latency between two adjacent guys times the diameter in order to get messages across the machine. And so I'm going to show you a picture of latency on the next slide, but where does the latency come from? Why does it take time to actually move? It's because the hardware has to do something, and the speed of light is we're usually way above that. It takes time to charge up a wire and get it to move across. But also there's a lot of software overhead where you have to pack up a message, get it to move and unpack it at the other end. So all of that counts as the latency too. So let me just go and show you the data. And the big observations that we'll see here is that there's 1 or 2 orders of magnitude differences across different networks. All of the numbers are between 1 to 10 microseconds, 1s to 10s of microseconds. So how many floating point operations can you do in a microsecond, roughly? Anywhere from 1,000 to 1,000,000. So one message is like 1,000 operations or 1,000,000 operations. So you don't want to send one message to tell somebody to do 100 operations, right? It's not worth the time. So let's go look at some data. So this is old data now, I have to admit. And so these are a bunch of different machines. So and it shows you both whose network and whose processor. So IB is InfiniBand. That's a commercial network that has newer versions. This is InfiniBand attached to a G5 processor, InfiniBand attached to an Opteron. They get different speeds, and the vertical axis is the round-trip latency. So how do you actually measure latency? You'd like to say it's the time to get from this processor to the other, but how do you measure when it arrives and when it leaves, right? There are different processors with different clocks. So what you do is you measure the round trip. You send it to somebody, as soon as he gets it, he sends it back to you, and you measure that and divide by 2. And that's how you do the benchmarking. And so you can see they're all, as I said, in orders of 1s to 10s of microseconds. So let me show you some historical data, because if you're used to computer science, you say, oh, it's just going to be twice as fast next year, right? No. So here is a picture, historical data, going back to 1990 up to 2005, which is when this is all the data I have. And the horizontal axis is years. The vertical axis is latency in microseconds from 1 to 100. And so is this doubling every year or halving every year? No. I mean, it's kind of flat. If you insisted on drawing a straight line through this and say, how much is the latency improving per year, you might say it's getting 5% better, but it's really just a big cloud of data. And it really hasn't gotten better since 1997. There was the Cray T3E, and that had like order microsecond latency. And so things are not improving dramatically. And so, but we know other things are improving dramatically because of Moore's law. And so this is going to be more and more ever the bottleneck, if you write code that insists on sending too many messages. Question here,
Why is it not improving?
Okay. Let me give you the microphone anyway. Short question, I'll repeat it.
Why is the latency not improving?
Because it's subject to different physical laws. So the time it takes to charge up a wire, which then has to go outside of the chip and go across a long distance and then get into another chip, is not improved by transistors getting twice as small every year, right? There's sort of more basic physical things going on. Just to give one more data point, I'm not sure it's quite on here. So the Earth simulator, which was the fastest machine in the world for a number of years in Japan, it occupied about 2 tennis courts worth of space. And I remember someone did the calculation which said that the latency on that machine was about 10 microseconds. The speed of light across the machine was about half a microsecond, if you just followed all the wires and just did speed of light. So they're getting actually pretty close to that limit for a machine of that enormous size. So so this is a different physical limitation. There's another question back there?
Are the interconnects always over copper, or are they ever optical?
Oh,
and does that give you a performance increase?
Yes. So optoelectronics is a big research area. There was in fact, a seminar just a couple of weeks ago by Vladimir Stojanovic from MIT, who's doing a lot of research in that. There are people here doing research in that. Yes, people are trying to change the technology. I can't say that there's something that's about to change the world, coming up soon. It's still a hard research question. And I think optoelectronics also has, I think it will drastically improve bandwidth. I'm not sure it will affect latency quite so much. So, but I'm not the expert there. Good. Any other questions? And then there's quantum computing and many other things that are even farther away that could make things go arbitrarily faster. But we can't afford to wait. Okay. So now let me put up some other numbers, which is the bandwidth. That was all about latency. And so as I said, the latency is the number of bits per second that go down a wire. And the thing is that that's limited not just by the electronics, it's also limited by how you have to pack it together to make sure that you can both forward the messages and make sure the messages arrive intact. And so what does a message consist of? It consists of the payload, your actual data. It consists of some routing and control stuff. So there's the forwarding address if it has to be forwarded to somebody else. When data goes over a network, it can be corrupted. Even data in your memory can be corrupted. So there's some codes at the end so they can correct it. So you can, typical is single error correct, double error detect. And then there's a trailer to say it's the end of the message. And so if you're sending very, very tiny messages in the tiny payloads, almost all of the bits are going to be either the header or the trailer, and you'll get a rather lousy bandwidth. And so, if you send very large payloads, then you'll get most of the benefit of the machine. So here is some data. And this is for sending 2 megabyte messages. So these are very large, so the data payload overwhelms everything else. For the same set of machines and networks that we had before, so for example, InfiniBand on a G5, InfiniBand on Opteron. And there's sort of 2 labels in the vertical axis. The first one is the percent of hardware peak. So this is, forget the software and all the packing and unpacking, just measure the raw hardware bandwidth. What fraction of peak do you get? And that's, some fraction of 100. And then these small numbers at the top of each bar are the actual speed that you get in megabytes per second. And those are not, so this is 244, that's 857. The vertical axis is percent of the hardware peak. So you can see that the hardware limits are quite different on all of these different processors. Now, if you insisted on, so if I were to draw the same picture that I did before, which is bandwidth as a function of time, it is improving over time. And it's getting better at about 23% a year, as opposed to 5 or not at all. So this is improving more. We can count on that, but it's still nowhere near Moore's law, right? Because the physics is still a little bit different. And so it is also increasingly becoming a bottleneck compared to doing the arithmetic. So let me just show you some more performance data. And so now what I'm showing, the vertical axis is the bandwidth, and the horizontal axis is the size of the messages that you're sending. And remember, the last picture was just for the really, really big messages, 2 megabytes, which is off the scale on this side, so enormous messages. Here I'm sending messages anywhere from a size 2K up to 128K. And I'm measuring how fast it goes. And so you can see that for short messages, it sometimes goes more slowly, and that's because there's all the overhead of packing and unpacking. And when the message gets large enough, then you actually get a large fraction of peak. And I'd like to point out to you the blue line and the pink line. Those are both the same hardware. They're both Cray T3Es. One of them is running MPI, which is one I'm going to recommend that you use. And the other one is running a lower level thing at the bottom called SHMEM, which is their shared memory emulator. And you can see that if you write the low-level stuff, you get the pink line, and it attains the peak bandwidth much faster. But if you're using MPI, it eventually peaks out at the same place because it is the same hardware once the message is long enough, but it takes a lot longer to get there. So that's the price you pay for portability and not writing machine-specific code. Okay. So the next metric that sort of determines what happens in a network is called the bisection bandwidth. And so all the data that I was just showing you is I have two processors. One sends a message to another. That's what I measure. And everybody else is quiet. There's no congestion. And that's the best you can hope to do. So I also want to have a measure of what can happen, how much worse will it get when everybody's trying to talk to everybody, which is what typically happens in an algorithm. And the metric is bisection bandwidth. So what that is you say, what is the worst situation if half the processors are trying to send a message to the other half of the processors? What is sort of the bottleneck, the place where the traffic jam occurs? And so if it's if I just have everybody connected to my nearest neighbor, it's clearly divided down the middle. And if the three guys above are all trying to send it to the three guys below, that wire will be the bottleneck. And the bisection bandwidth is just that one wire. So, but what if I have a two-dimensional mesh, and people now build three-dimensional meshes? Then the question is, what's the worst thing I could possibly do? It's if everybody above, again, this line drawn through the middle, since it's nice and symmetric, tried to simultaneously send everybody to the bottom. So I would have these, n squared p over 2 processors communicating with p over 2 processors, but only over the square root of p wires. And so here, the bisection bandwidth is going to be the square root of p times the bandwidth of a single link. Here, it's going to be a single link. And so depending on your algorithm, you may be limited by this as well. And this is why people build lots and lots of different topologies. And so in the past, as I said, there's been a lot of research in these topologies, and I'll just show you a few pictures to show you the history. And people were trying to minimize both the number of hops it took to get from one place to another and have a good bisection bandwidth. Modern networks try to hide all this. They use what's called wormhole routing, so they will sort of try to find the fastest, least congested path on the fly and send it to you. And so most of the time you don't have to pay attention to this, but this is sort of the dive into the hardware part of the talk. And there are a few algorithms where it really does matter. So let me just show you some of the topologies that people have used and what the bisection bandwidths are. And so here, it's the linear array. That's the simplest thing you could have. The diameter is n minus 1. That's the distance from the left to the right. And if you pick two random processes and ask how far apart are they, you can do the probability theory. It's about n over 3. So it's proportional to the number of processors. And the bisection bandwidth is divided down the middle. It's 1. And if I make it a torus or a ring, it improves by a small constant factor. But so if it's a one-dimensional connection, that's all you get. So here are the two-dimensional ones, which people started building. And it can either be just a plain old mesh, in which case there is the bisection bandwidth, as you cut it down the middle there. But typically people build tori, so you're connected around, the two ends on the left and the right are connected, and the top and bottom are connected around, so you don't have to worry if you're near the boundary or not. And their thing, that improves everything also by a constant bandwidth. And as I said, the old machine at NERSC, that was Franklin, now Hopper, that uses a 3D torus. IBM Blue Gene has gone from 3D to 5D. So people also did hypercubes, and this was, there were many famous machines, the Intel, IPSC, the N-Cube, companies that are, some of whom are no longer with us, built machines that looked like this. And so one of the reasons people liked this is there was a very clever routing algorithm. So the question is, how did you decide how to get from one processor to another? So suppose I want to get from processor 000 to processor 110. How do I decide which set of wires to go on? Well, I compare it bit by bit. 0 is different from 1, so I take one step along that wire. Then I look, 0 is different from 1, so I take another step along the next direction. And then I compare 0 to 0, and I know I'm done, so I don't go anywhere. And so everybody is sort of, if everybody goes somewhere else, you just do it bit by bit, and it's a very simple store and forward. People like that. Now, here is something maybe a little unusual. I mean, it's a tree. That's not unusual. And it's pretty clear that if I had a tree where every wire had equal capacity, then and if all these guys wanted to talk to these guys in the left subtree to the right subtree, the root would be a bottleneck. So how do you fix that? What you do is you double the number of wires at each level of the tree. So that is actually one wire, each of those. Above that, those are actually 2 wires wide. At the next level, they're all 4 wires wide, and at the top, they're 8 wires wide. So at every level, you can actually take all the information from your left child and the right child and push it up through the tree, and it works. And this was actually built in the Thinking Machine CM5. And what they had to ask themselves is, how do you lay that out on a plane? So this was just an interesting geometry problem. So here is a perfect binary tree laid out in a nice two-dimensional mesh. And you can convince yourselves by looking at this that this nice, simple recursive structure is actually the same thing as a tree, and it fits very well. You can build it out as big as you like. And it also maps to this fat tree, because every time you go up a layer, you double the number of wires. So you go from 1 wire at the bottom, then 2. This should have been 4. This should have been 8. I kind of abbreviated it to make it all fit on the screen. So this is what people built as well. Then those are called fat trees. Now, then I mentioned butterflies. And this was invented because of the fast Fourier transform. And so we'll see this picture again when we get to the fast Fourier transform. And there was a machine, the BBN Butterfly, that built, again, a company no longer with us, that built it this way. And so here are the processors. And I have 8 processors, and I've drawn them 4 different ways, but you can think of each of these being the same. And so the question is, how do I route from one processor to another? Suppose I want to get from processor 5 to processor 6 along this butterfly. So if you look at this, there's this pattern where you have 2 processors in, 2 processors out, and they're connected either directly or with this cross. So this picture here is just repeated over and over again. It appears here. Here they're kind of interleaved. So these 2 processors and these 2 processors are connected in this same little butterfly. So how do you do the routing? Again, you say, here's my source, here's my destination. You compare it bit by bit, going from left to right. If the bits agree, they're both 1, I will simply go along the vertical line. I'll go from processor 5 to 5. Then I look at the next 2 bits, 0 to 1. They differ. So that means I don't go straight. I take the diagonal out from wherever I am, and I end up there. And then I look at the last 2 bits. They disagree. So I follow that wire, and I end up there. And that is my destination. So that should be processor 6. It doesn't look like processor 6. It's actually processor 6 if you reverse the bits. If you take these bits and do 0, 1, 1, that's a 3, and you are in processor 3. So it does bit reverse order. So this is one of the things that makes FFTs interesting, that the answer comes out in bit reversed order. But it still works. OK, so I've been telling you about all these topologies. And as I said, MPI hides it from you almost all the time. And that's because most of the time people build the hardware so they don't want you to have to pay attention to it. And the question is, does it ever matter? So let me just show you one experiment which actually started as a class project in here and then ended up as a supercomputing paper with the world's fastest matrix multiply, because it was the bottleneck in matrix multiply. So this is a 1 megabit multicast, which is sort of, I have to send data from everybody to everybody else. It's like a transpose. And it's showing you how fast it went on 3 different machines, an IBM BGP, and 2 different flavors of Cray. All of these are 3D tori. They all have the same topology. And so what I'm measuring here is a function of the number of nodes, what's the bandwidth. And for these 2 machines, the bandwidth went down as you added processors. But for the IBM, the bandwidth went up, even though they have the exact same, in principle, 3-dimensional torus interconnect. And that's because the algorithm on this machine actually paid attention to the fact that it was a 3-dimensional torus and used all the wires all the time, and it went faster. And for these particular platforms, the algorithm did not, because when you asked for 512 processors, you may have hoped to get an 8 by 8 by 8 torus, but you sort of got them spread out randomly across all 150,000 processors, so it really wasn't connected in a torus, and so there was a lot more congestion in it. And so sometimes, if you're interested, this is, you have to pay attention. Most of the time, you don't have to pay attention. Okay. So let me just finish. This is the last slide on the hardware stuff, which is how these machines have evolved over time. When they first built them, the CPU was responsible for everything, doing all the useful arithmetic and being the postmaster, reading the incoming mail, forwarding it if necessary. And so that has certainly been replaced by special processors who are responsible for being the postmasters. And so so it's direct memory access. And so that means the processor, that particular special processor can take the messages and it can put it directly in the memory where it belongs without ever interrupting the CPU. So the CPU doesn't even have to ask, did it arrive? I mean, you'll get race conditions if you don't, but it all will just sort of get put into memory where it belongs when you want it. If you send it, you can send the data to any processor you want. This special separate processor will do all the forwarding. It'll be the postmaster, and it'll sort of, it's called wormhole. It'll just find the quickest path to the network that it can. And all of this is hidden under the covers in MPI. So that's the end of the hardware stuff. And so now I'm going to give you a very simple mental model of what you need to know about all of this for most programs to estimate the cost so that you can say, is my program likely to run fast? So are there any questions about that before I go on to performance models? Okay. So we had a performance model for shared memory, and it was called PRAM, where communication was free, and that's too good to be true. So the question is, we want to have a nice, accurate model that uses as few parameters as possible. It tries to capture all that complexity of all that hardware I was showing you about. So PRAM, where communication is free and everybody can talk to everybody all the time, that's good for doing certain kinds of theoretical analyses. But if you want to actually estimate how fast your code goes, you need something else. And so we're just going to have a two-parameter model, which is the latency and the bandwidth. And so what I'm going to say is that the time to send a message of n words from one processor to another is going to be the sum of two terms. The first one is the latency. That's the time for the beginning of the message to arrive. And then n times the cost per word, which is the n divided by the bandwidth. That's time for the rest of the packet to arrive in the network. So I'm going to assume they're all packed together, moving as fast as possible. And I'm going to ignore the topology. And I'm always pretty much going to use alpha as an abbreviation for latency and beta as an abbreviation for the reciprocal bandwidth. So this is going to be my model. And because of all of those hardware trends that I told you about, alpha, the latency, is the biggest guy. He's a microsecond at best and not getting much better. That's a whole lot bigger than the time per bit, which is going at hundreds or thousands of megabits per second. And then if you have the time per flop, that's your teraflop that you're doing on your processor. So that's even a much, much tinier term. So clearly I want to minimize the amount of communication. So the simplest thing you could imagine doing is notice that if you're sending many, many short messages, and let's say you want to send n messages of length 1, what would that cost? Well, there's n times the cost of one message, the latency of one message plus the cost of that one word. That is a terrible idea if you instead have the option of packing them all into one. Right? If you can pack all n words into one message, the cost is one latency plus n times the bandwidth. So you get n beta on both sides, but you have alpha there and n alpha there, and that can be the lion's share of the cost.
In that analysis of the one message case, are we saying that if I send the first message, I have to wait for that to complete before I start sending the next message?
Yes, that would be that is the assumption of this model, that they don't overlap, and so the question is that an accurate model or not? And it's a good thing you ask, because that's the last line on the slide. People have tried to have more sophisticated models that capture more of the potential of overlap, and that's called the log P model. And in that case, you separate out the latency and the overhead. Some of this can be overlapped, some of it cannot. But you'll see when I show you the data that for our purposes, a two-parameter model is rather simpler than this four-parameter model. So I just want to have the simplest model that that's useful for us. But you can always do better. So let me just show you lots of measurements on a slide. And I've done this for many, many different machines. And we measured the alpha for all those machines, and we measured the beta for all those machines. And we measured the alpha by sending a single one-word message and ping-ponging and asking how long the round trip takes. And then we measured the beta by measuring how long it takes one huge message to arrive. And so what I'd like to do now is actually take the real data and compare it to the models on all these machines and ask how well does our really simple model, which is alpha plus n times beta, map reality. So let me show you on one plot for all these different machines what the model predicts. So here is what it looks like. And so the horizontal axis is n, the length of the message. The vertical axis is time. Each of these curves is a different one of those machines in the previous slide. And so there are obviously two phases. In this phase, alpha is dominant. And so when you do alpha plus beta n is so small it doesn't matter. And so these terms are all alpha. And when n gets really large, it grows linearly. In this case, the beta n, you get a straight line with slope beta, and the alpha doesn't matter anymore. So this is what is modeled. And now let's compare it to the measure. And I'll just sort of go back and forth. So there is modeled, and there's measured. So they're about the same. So there's obviously a little irregularity. Measurements are always irregular. But the takeaway is that this two-parameter model is good enough for us. Okay, and that's what we're going to use when we analyze algorithms later. Okay, so are there any questions? Microphone, here, I'll do it.
So to calculate the alpha and the beta, do you take the average of between all the pairs of processors and stuff?
I'd have to go back and look at how this experiment was done. I think what it was done, you took two processors kind of at random, and then you did the experiment many times between those two processors and you averaged, because it's always a little bit random from one to another. You should always repeat experiments and take averages.
Also, regarding the bandwidth, was it under what scenario, as in what sort of congestion or what sort of traffic load was it?
So in this case, the experiment was done very carefully on an uncongested machine. So you got your own chunk of it, and you were not sharing it. That can obviously decrease your beta. So this is sort of a best case scenario. Shared resources are always interesting, right? So no surprise. So do we want to comment on Hopper and when you do your homework and how shared that resource is?
You're going to reserve some number of nodes. So for the matrix multiply assignment, since it's single threaded, you obviously only need one node.
No sharing.
No sharing. But for the other assignments, when you do, say, particle simulation with MPI, you'll get a number of nodes, and you'll have all of those to yourself. Now, I don't know how the network topology works. Like, I don't, because it's probably some kind of store and forward low-level routing. Who's to say if you're routing packets from, someone else's job? But it shouldn't
Right.
affect
It has
performance.
not proven to be an issue in the measurements for this class in the past at the scale to which we ask you to do scaling. So when people do the top 500 and try to say, am I the fastest machine in the world, they get the whole machine to themselves. So there's no question that there's no contention there. OK, so now we're going to go on to actually how to write the code in MPI. And so people have built these message passing libraries for many years, and with many funny names. Some of them were public domain, like PVM. Some of them were commercial. But finally, people got tired of everybody spelling send and receive slightly differently, so they formed a standards committee. And there is now a standard way that everybody's agreed on. And books have been published, and there's standard implementations that you can download. And whenever you go to a particular parallel machine, like Hopper, somebody will have already implemented a particularly well-optimized version of it for that machine. So this is MPI. So the way these libraries work and the way you're going to write the code is you should imagine that you write one program and you simply get P copies of it all running in parallel on all the different processors. Each one only sees its own memory. So whenever you refer to a variable, it's yours. There's no shared data. And so the only way that you can synchronize or communicate with another processor is you have to have subroutine calls. So all the communication, all the synchronization happens by calling subroutines to do that. And so there are three things to do. There's subroutines for communication. The simplest ones are send and receive. You have one processor does a send from 0 to 1, processor 1 does a receive, and the data will pass. But there are also all those collectives I told you about. There's broadcast, there's reduce, there's a lot of variations on them, scatter and gather. I'll show you pictures of those later. And then there's prefix sum and so forth. So lots of subroutines for that. For synchronization, there is a barrier function, but you'll hardly ever want to use it. The only thing that barrier is really good for is timing. You do a barrier, you run your code, you do another barrier, and you call the timer to figure out how long it went. That's like the main purpose of a barrier. And there's no reason to have locks because there's no shared variables to protect, right? There is no shared data. And then there are a bunch of subroutines for inquiries. For example, how many processors are there? Which one am I? So you know which subset of the work to do. If you don't want to sit at the mailbox waiting for data to arrive and spend a lot of time there, so you could say, are there any messages waiting? Who are they from? So the way that MPI is organized is that you need to have to create sort of separate societies of processors so they can communicate among themselves without interrupting anybody else. So suppose your job is to write a subroutine library for doing linear algebra, and somebody else has written one for doing FFTs. You don't want linear algebra messages to be delivered to the FFT library, because that's just everything will get confused. So you want to be able to define communicators which have separate domains of communication so that people can write code separately and glue it together later, and it'll all function correctly. So there has to be some syntax and some semantics to define communicators, separate societies of communication. Then there's lots of data types. I mean, people don't only send floating point numbers or integers. They're more complicated things that are built into the library. It's also interesting because not every processor agrees on how to store an integer. You can run MPI on a heterogeneous machine. You could run it across all the different processors in your lab, and it will work because when an integer is stored in one machine differently than another, the MPI will understand that and flip the bits around in the right way. So there are different modes for buffer management. So as I said, when you send a message and it returns, do you know whether it has actually been delivered? Do you know whether the buffer has been copied off into the network so you can overwrite it? Or is it still, when it returns to you, you can't even touch that data anymore because it's still being copied into the network? So there are all these different modes that you get to specify. They're the collectives I told you about. You can give hints about the topology. You don't have to. But if you know you have a certain kind of tree or 3D network, you can give a hint to MPI to help it go faster. And then what's really useful, and we'll have a lecture about this later, is that the interface has encouraged people to build special tools so that you can call a special version of MPI and it will give you feedback on how many messages you've sent. Where are the bottlenecks in your code? You don't have to do that yourself. There are a lot of special tools that will do that. And they rely on the fact that everybody's agreed on how to spell send and receive. And we'll hear more about that later. So the standard itself is available at this particular site. It's hundreds of pages long in the manual. I'm just going to tell you about 6 subroutines you really have to know in order to write code that works. And there's many online documentation, tutorials, and so forth, and whole books you can download or buy. Okay, so the first thing that you got to know is how do you find out how many processes are there and which one am I? Right? Those are the 2 most basic things to do. And there are 2 functions that will return that data to you. One is called MPI com size. So you can call a subroutine. It will tell you how many processors there are, so you know how many divided up. And then there's something called a rank, which is a number between 0 and size -1. Every process gets a unique value. So let me do the simplest thing in the world, which is almost hello world. So here it is in C. You have to include these header files so it knows it's running an MPI program. All MPI programs have 2 input arguments at the top. You just sort of put this stuff in, and I'll tell you what they are in a moment. The very first subroutine you should always call is MPI initialize, so it sort of sets it up, figures out who else is out there, and you pass it in these 2 arguments. So one of these arguments is probably the number of processors, right? And I'll show you what the line that you type in your shell script what this looks like. One of these is the number of processors. Then you can call MPI com rank, and then you have to pass in a communicator. Which subset of all the processors am I interested in? And this is the keyword for just tell me about everything that I've been given. So the world, all 64, 128, whichever ones I've asked for, and return the value, how many there are, and return the rank, and then return the size. How many are there total in this communicator, which consists of everybody? And then you can do a printf, I am number rank out of the whole size. And so you will get 64 versions of this. I am number 0 of 64, 2 of 64, and so forth. And then at the very end, you have to release all your resources. You call MPI finalize, and you're done. And I'm giving you examples in C, but if you go to the website, there are hidden slides showing you the syntax in some other languages. So let's just talk about that. So as I said, all MPI programs begin with init, and they end with finalize. MPI com world is sort of the default. It just says, I want to know about all the processors. But as I said, if you have a subroutine library, it'll have its own communicator for a subset. Just think of each program that I just showed you here. It sort of runs sequentially on each processor. So it's just sequential code, but you may have 64 copies of it running. And so I haven't really said too much about how I/O works. And MPI has gone through many different versions of the standard. And in the first standard, they kind of assumed that I/O could only be done by process 0, and it was your responsibility to get everything to process 0, and it did it all. Now you can have every process do prints or access files or whatever, so you can have parallel I/O. I'm not going to tell you very much about parallel I/O during this course. I mean, there are too many other things to talk about. And so how do you actually start that program? Excuse me. And get it to run on a certain number of processors. So you take your program, you compile it, you create an a.out file, and then you do MPI run minus the number of processors equal to 4, or whatever you want, and then a.out. So you'll get 4 independent copies of a.out running. And that 4 will be passed in as one of the input arguments. OK, so those are the simplest things you need. Now let's do some communication. And so we have to do sends and receives. And so let's suppose that process 0 has some data. It wants to send it to process 1. And so it needs to call send with enough arguments to make it work. And this guy has to call a receive. And so what do we need to do? We need to somehow specify what the data is. We have to identify who is going to be the receiver, because process 1 has a name, but it could be that he's willing to receive data from anybody, not just process 0. And process 0 has to say who it's going to. It may be that there's a whole bunch of messages being sent from process 0 to process 1. He only wants the one that has this particular data, so you can have sort of screening in there to filter out the data that you don't want. And then how do you know when it's done? You know. So here are some concepts. As I said, that the communicator comm world is just everybody that you get. You know, all 64 processors that are allocated to you. But you know, just as society has to be organized into groups that communicate with one another without spreading all their information around, you need to have a hierarchy of communication in parallel too. So all the groups in a communicator they're broken down into groups, and each group in turn has another layer of hierarchy called a context. And over time, people decided that 2 layers of hierarchy were enough. And the examples I'm going to show you, there's only 1 layer, comm world. But if you want to build something more complicated, you can break down all the processors you get into groups, and those can be broken down into contexts. And so then you specify the name of a group and a context together in the communicator, so when you do send, you have to specify this. And so only the other processes that are part of this group and context will get the message. Otherwise, you know, if all the mail went to everybody, there would be just, it would be very hard to write things, or write correct code. Excuse me. So now, let's talk about data types. So I want to specify a data type. So I have to say where it begins in memory. I'm going to copy it out of my local memory. How much is it? And what's the type? Is it single precision floating point numbers, or the integers, or whatever? But MPI lets you define rather complicated ones. And so it has some that are built in, like MPI int, MPI double. It knows about those. You can send a contiguous array of them. So that'd be like a row of a matrix in row major format. But you might want to send a column of a matrix in row major format. So you want to take every nth entry of that, so it has the ability to do striding. You can have sort of general arbitrary index things. And you can build structs. And it will automatically pack and unpack it for you. But you can imagine it gets complicated. Suppose you want to send a linked list from one processor to another, right? So you have pointers, which are memory locations. What does it mean to send a linked list and have all the memory pointers still work? You have to build some of these yourself to sort of interpret what it means when it gets unpacked on the other side. But those are all possible data structures. And if you send something that's really complicated to pack and unpack, it will slow down. The other thing that you can do is there's a third level, if you like, in this hierarchy of contexts and groups. And now we have tags. So it's a third level. You can say every message is going to come associated with a tag. And you can say, I only want to have accept mail with a certain tag on it. Or you can say, I'll take any tag. Or you can use a wildcard. And so all the examples I'm going to show you, I'm just going to use any tag as the wildcard, because otherwise it just gets too complicated. So all of these have been put in as, you know, why is there this complexity? It's because as people tried to build bigger and bigger systems, they needed to be able to break things apart and work independently. These let you work independently. So here's the simplest example of a syntax for doing a send. It's called a blocking send. It's called blocking because it won't return until it's actually been delivered. So processor 0 does MPI underscore send. It's going to send data from memory starting in the in array A. It's going to send 10 words. They're going to be double precision, and it's going to be sent to processor 1. That's the address. And so, in addition, there's excuse me, a tag which I haven't written in, and the name of the communicator. And we can just assume it's MPI com world. And so these first three words are the start, the count, and the data type. MPI, on processor 1, I'm going to do a receive. And so I'm going to receive the data. Where am I going to put it? When it lands, I'm going to put it into array B. That's my local array. I'm willing to accept up to 20 words. I can take fewer. I can ask how many actually arrived after that happens. But I'll get an error if you try to send me 21. And they're going to be doubles. And I'm expecting them from processor 0. That could have also been a wild card. I could have accepted them from anybody. And again, I'll take them from any tag. And so when these functions better be called in a pair, because if you do a send and this guy doesn't do a receive, you're just going to hang. Excuse me. And so these have to come in pairs, but when they return, you are guaranteed the data has been delivered. So that's not always the way you want to do it, but in this particular flavor of send and receive, it's blocking. The receive is similar. You say, where do I want to put the data when it arrives? How many words am I willing to take maximum? What's the data type? Where is it coming from? What's the tag? What's the communicator? And there's a status, because you want to know what happened when it's all done. Because you may not be sent 20 words, but you can look it up when it's all done by looking it up in that particular return value in the status. And so for example, status.length will tell you what the length is and so forth. So let's write a simple program. And so this is going to be, I'm just going to send a number, the integer 1, 2, 3, 4, 5, 6. I'm going to send it from processor 0. I'm going to send it to processor 1. So here I call MPI init. That's the first thing I have to do. I declare the status to be this type, so I can go look up inside that structure when it's all done. I get my rank, so I know am I number 0 or am I number 1. And so now I say if I'm processor 0, I do this, I do a send. Else, if I'm processor 1, I do a receive. So you have to have both cases written inside your code, because the same code is executed both on processor 0 and on processor 1. So you have to have this if statement. Depending on who you are, you do the right thing. So if I'm processor 0, I do a send. And else, if I'm processor 1, I do a receive. And then I print the fact that I got it when it arrived. So that's a really simple code. So what can I do with the status? Yeah, please ask questions about what this looks like. So you can see it's kind of low level, but it's portable. Life is trade-offs. Question? Here, I'll pass. Oh, you got it.
So far, it looks like your regular IPC or sockets or any communication protocol, but MPI scales from the same machine to many machines. So
Hundreds of thousands or more, yes.
So then how does it know? I'm assuming that like the format for message passing should be standardized, but then you have trade-offs of passing on the same machine where you don't need this header data versus many nodes where you need the extra header data. Is that all low level?
So the MPI does have a scaling issue, which is that I believe that in most implementations you need to have a local table of size proportional to P, so you know where all the other P processors are. And you can have some status associated with each one as to whether something has been sent or received. And so when you start scaling up to very, very large numbers, MPI does have that sort of internal memory bottleneck.
So, but does it know that processor number 5 is in the same chip versus number 10 away?
So there are versions of MPI which you can run on shared memory machines, and they know that you don't actually have to send a message. You can do it just by copying to data. So that way you can write one MPI code and run it on your multi-core platform or on your big distributed memory machine, and you don't have to change your software. Now, what if you have, like on Hopper, you have 24-way parallelism locally on your chip, and then you have thousands of those. So what people, MPI will not do the perfect thing necessarily. So what people have been doing, alas, is they have one MPI process per chip, and then they write OpenMP code to access all the 24 cores on that chip. So you write one OpenMP program, so this would be OpenMP, and it calls MPI init, and so forth. But then it could generate 24 threads inside of itself. So that's not perfect, but that's what people do today if they want to get the maximum performance. You could also write one MPI process per core, then you'd have 24 of those running on per node. But then you're going to use up a lot of your local memory and resources to keep this track of everything. Does that answer your question? Okay. So as I said, status, when it returns, you can look up stuff to find out what happened. So for example, you can say, what was the tag? If I said, I'll take any tag, you can go look up and see which one it actually was. If you're willing to take the data from anybody, you can say, who actually sent it to me? You look at the return address. And you can actually figure out also where did it come from and all these different things. So that's what the status is for. What am I doing here? OK. And as I said, there are tags and contexts. There are 3 levels of hierarchy in these communicators. And for the programs that you have to write, you don't have to worry about this. You're only going to use sort of the one level MPI COM world. But in practice, to write big codes that you can share with other people, use libraries, then you have all these 3 levels of hierarchy that people use. So I'm going to stop soon, but let me say here are the 6 subroutines. These are really all the ones you need to know to write correct MPI code. It won't necessarily run the fastest. You need to initialize at the very beginning. You need to finalize when you leave. You have to find out how many processors there are and which one am I, and their send and receive. And next time, what I will do is talk about 2 more, which are the broadcasts and the reduces. And so you can, so maybe there are 8 that you need to know. So we'll stop here.